Hello everyone, and welcome back to another mathematics tutorial. Today I'm going to be talking about supremums and infimums of sets of real numbers. These are very important concepts, and it's important to understand how they work and what they are. Now, on the screen, I've said let E be a subset of the real numbers. Okay, so E is some subset of the real numbers. Now, we're going to look at a concept called an upper bound. Okay, now you may have seen this before, but an upper bound, so we say y in R is an upper bound, so I'm going to write UB for upper bound, is an upper bound for E if for every x in E we have x is less than or equal to y. Okay? So y is just an upper bound. It just bounds things from above in E. Okay? So e.g., if E is equal to, say, the set 1, maybe 3.5, 4, okay? Then 10 is an upper bound, for E, okay? Because 10 is bigger than or equal to anything in this set E. Now, the supremum is a special kind of upper bound, okay? So, we say y is the supremum of E if for every upper bound of E, so for every upper bound E, let's call them D, okay, we have y is less than or equal to D. So, in a sense, y is the smallest upper bound. Okay, it's smaller than or equal to any other upper bound of E. You might also hear this called the least upper bound, because it is the smallest upper bound. Now, I'm going to go over a few examples of this, because it can be a bit abstract at first, and some concrete examples will help you to understand the definition. So, if we take our set from before, so we had 1, 3/2 and 4, then the supremum is going to be 4. Okay, and when you want to write down the supremum, you write this notation. So you write sup, S-U-P, and it's pronounced sup. So sup E is equal to 4 in this case. Okay. And we can just check this fairly easily. So 4 is definitely an upper bound, because it is bigger than or equal to everything in the set. So 4, so for every x in E, x is less than or equal to 4. Good, because x can be at most 4. And also, if there's another upper bound, it has to be bigger than or equal to 4, right? So if D is an upper bound, for E, then D is greater than or equal to 4. So we've found the supremum is 4. It's the smallest possible upper bound. Okay? Let's try another example. Let's try a little trickier example. So maybe E this time is equal to everything between -1 and 1. So with a little diagram, here is 1 and here is -1. Now there are quite a lot of upper bounds for E, so 2 would be an upper bound, and so would 1.5, and so on. But the supremum of E, is 1. Because it is an upper bound, definitely, because everything in E is smaller than or equal to 1. But also, if I try to go smaller than 1, if I come in here, I can find something in this interval that's bigger. I can just pick, say, here, and it's going to be bigger than whatever I've chosen that's smaller than 1. Okay, so 1 is going to be the supremum, the smallest upper bound. Okay? Let's try one more. Okay, let's try e is equal to the set of 1 over n, such that n is in the natural numbers. Okay, so this is basically, it's 1, a half, a third, a quarter, and so on forever. So n ranging over all natural numbers here, starting at 1. What is the supremum? Well, supremum of e is again 1. Because 1 will be an upper bound, as you know, as n gets bigger here, this is just going to get smaller and smaller. And then also 1 is here, so if it's an upper bound, it's going to have to be larger than or equal to 1. So the supremum, the smallest possible upper bound, is 1. Okay, I hope that explains the concept of supremum. Okay, I will be doing some more detailed videos on it later, but the next thing I want to address is the infimum. Okay, so the infimum is a similar idea, but it's now talking about lower bounds. Okay, so we say, let's go for z this time, is a lower bound for e, so this is LB now, a lower bound for e, which is a subset of real numbers, if for every x in e, z is less than or equal to x. So z is now a lower bound, it's bounding from below. And we say z is the infimum of e if for every lower bound, let's say alpha of e, we have z is greater than or equal to alpha. So z here is the greatest lower bound. It's the biggest possible lower bound you can have. Okay, so going over an example, if we're taking -1 and 1, then the infimum is -1. Okay, because -1 is a lower bound. Okay, -1 is a lower bound because everything in between here is going to be bigger than or equal to -1, and -1 is the largest possible lower bound, because if we start going down here, looking at -2, then it's going to be smaller, because we're going more negative now. So -1 is the infimum. Okay, so the infimum is just the greatest lower bound, the largest possible lower bound. Let's try an example. What if we take e is equal to our set 1 over n, such that n is in the naturals? So again, that's just 1, a half, a third, and so on forever. What is the infimum? Well, we found that the supremum was 1, but what about the infimum? Well, here the infimum is going to be 0. You write inf here, so inf of e is equal to 0 for the infimum. So the infimum is going to be 0. Why is that the case? Well, this 1 over n is just going to get smaller and smaller, and in fact we can say that 1 over n goes to 0 as n goes to infinity. So 1 over n is going to get extremely close to 0, and so 0 will have to be the infimum. Okay? Because, you know, if you pick something that's bigger than 0, then 1 over n is eventually going to become smaller than that. Okay? So the infimum here is 0. Alright, now there's an important axiom which I will briefly explain now, and I will do a further video on it to make it more clear later. But it's important to remember that some sets might not have a supremum. Okay, some sets may not have a supremum. So if I took E is equal to 1, 2, 3, 4, forever, okay, so it's all positive whole numbers, then the supremum of E does not exist, because there is no upper bound, is there? There's no upper bound. If, you know, I will just get bigger and bigger. So, you know, if C is an upper bound, then just take the next natural number that's bigger than C. So, you know, e.g. C is 2.5, then 3 is greater than 2.5, so it's a contradiction. So it's a contradiction. So there's no supremum, there's no upper bounds, and therefore there is no supremum. So sometimes the supremum might not exist, and the same is true of the infimum as well. But there is a case when the supremum does exist. So let E be a subset of the real numbers again. Then, if E is not empty, okay, so this means E is not empty, and E is bounded above, then the supremum of E exists in the real numbers. Okay, so this is telling you that if E is not empty, so there's at least one thing in E, and it's bounded above, then the supremum exists and is some real number. And this is called the completeness axiom, or the completeness of the real numbers. Okay, so e.g. E is equal to the set of all x in R such that x squared is less than 2, then, well, is E non-empty? Yes, 0 belongs to E, because 0 squared is 0, which is less than 2. And, well, let's have a look here. For every x in E, we can say that x is less than or equal to, say, 10. Okay, because we want x squared to be less than 2, so certainly x has to be less than or equal to 10. So it is bounded above by 10, and it's non-empty. So sup E exists. And with a bit of work, you can actually show that the supremum is the square root of 2. But that's another matter. So I just want to show that this example showing that the supremum exists using this axiom up here. Okay? And there's a similar one for the infimum as well. Okay? But I'll leave you to figure that one out on your own. But this is the important one. You want to know the supremum exists. Okay, I hope that cleared things up on supremums and infimums. I'll be uploading some more videos detailing properties of supremums and infimums later on. Don't forget to subscribe, and I'll see you next time.